Okay, you two, let's go back to the birth of the universe. Things are hot, real hot. And things are happening fast, real fast.
For the tiniest increment of time that is possible to talk about, 10 to the minus 43 seconds. The temperature was 10 to 32 degrees, and the density, downright indescribable. At that instant, there was only one universal force and one type of elementary particle. But it wouldn't last. At the end of this instant, gravity separates itself from the union. At 10 to the minus 35 seconds, the strong nuclear force exits the union as well, and this triggers inflation, the event where the universe instantaneously grew into size, from tinier than an atom to an unknown large size. This expansion and subsequent cooling down to 10 to 27 degrees allows 6 different types of quarks to form. At 10 to minus 12 seconds and 10 to 15 degrees, the weak force and electromagnetism separate, and we have the 4 independent forces we know today. At this point, all 6 types of leptons have formed, including the electron. At 10 to the minus 6 seconds, up and down quarks have formed protons and neutrons. All heavy quarks have decayed. All heavy leptons have decayed. All antimatter has disappeared. And by the time the universe is only 1 second old, protons and neutrons are already getting together to form the lightest atomic nuclei.
Wait! Can you slow down and try that again?
Sure, Diana. Can you tell me the difference between force and matter?
Well, sure. Matter is stuff that you can hold in your hand, or at least visualize holding in your hand. And a force is something that causes matter to move, change, or react, an action. Air is matter, even though you can't see it unless you're in Los Angeles.
Pretty good. Now, consider a piece of matter, and imagine taking it apart down to its basic constituents, the particles that make it up, down to the atoms, and further down to the protons, neutrons, and finally to the quarks and electrons. If our hands were small enough, we could hold them in our hands as well. So, these particles pass your hold-it-in-your-hand matter test and are declared matter. But at this level of tiny, things get a little fuzzy. Watch this.
As we take apart matter, down to the smallest scales, we must pass through levels of structure that are only possible because of forces that hold these structures together. The proton and electron, for example, are attracted to each other, and that force of attraction is what holds them together in the atom. But what is it really that causes this attraction? How does the electron know the proton is there? And what draws it towards the proton? How does the electron know not to be attracted to the neutron? The answer is that the electron and the proton each fill the space around them with countless millions of other tiny particles that have only the most ephemeral existence. Because it is electrically neutral, the neutron does not. These particles come into existence only briefly and are gone, only to be replaced by another one thrown out by the parent particle. On this scale, the tiny bit of energy that is needed for the existence can be created out of nothing. But they also must disappear in the briefest instant, because the energy used to create them can only exist for a very brief instant. You can imagine these virtual particles as balls tethered to the parent particle by a rubber band and snapping back to the parent when they disappear. If one or more of them should encroach upon the territory of a virtual particle tethered to another parent particle, they can get entwined and exchanged. Such an exchange is felt by the parent particle as a force.
These fields of virtual particles surrounding a parent particle are created in very specific patterns and fill the surrounding space in a well-defined way, and scientists cleverly call them fields. The virtual particles are called carriers or mediators of force.
Scientists recognize 4 distinct kinds of force fields, and they all work through the mechanisms described above. You are readily familiar with 2 of these forces: gravity and electromagnetism operate on a scale that we encounter in our everyday life. A third force causes quarks to stick together in protons and neutrons, and a residuum of this force causes protons and neutrons to stick together in the nucleus of atoms. This force is called the strong force, or sometimes the color force. The fourth force causes radioactivity and is called the weak force. The virtual particles that make up these fields and get exchanged in each force are called gauge bosons. And each of the 4 forces has its own gauge boson. Within limitations, energy and mass can be created out of the nothingness of space-time, but only for a very brief instant. And the more energy and mass these virtual particles have, the shorter must be the time that they can exist before snapping back to the parent. Lighter gauge bosons can exist for a longer time, and these in turn can get further from the parent before they must return. So the range of a force is directly related to the mass of its gauge boson. The photon is a gauge boson for the electromagnetic force, and the graviton is the gauge particle for gravity. Both of these particles are massless, and so the range of these 2 forces is unlimited. The strong force is much more complex. The charge property responsible for the force between quarks comes in 3 distinct states. Not just 2, like the positive and negative charge states in electromagnetism. So in a loose analogy to the 3 primary colors, red, green, and blue, the 3 kinds of charges in a strong force are usually referred to as color charge, and are designated red, green, and blue. Since the theory of electric charge is dubbed quantum electrodynamics, or QED, the name for quark theory has become quantum chromodynamics, or QCD. It is interesting to note that all observed particles are white. Color is never visible. And since the proton and its baryon cousins each have 3 quarks, the color possessed by the 3 quarks must be 1 each of red, green, and blue, which sum to white. And mesons are always a quark and an antiquark pair, containing colors of red, anti-red, or blue, anti-blue, or green, anti-green. also combinations that equal white. The strong force, of course, must have its own gauge boson, and it turns out that there are 8 of them. 8 different gluons that carry the color force. And unlike the other force carriers, gluons have a color property themselves, and therefore interact with each other. Every time 2 quarks interact and exchange a gluon, they swap colors. Also, because gluons are attracted to each other, it is possible to have a gluon collection, which is referred to as, what else, a glue ball. The interactions that result from the weak force are incredibly short-ranging. They are effective over a distance even smaller than a proton's diameter. And this accurately implies that the weak force gauge particles, called the W and the Z, are immensely heavy. Over distances small enough and at really high energies, the 4 forces are indistinguishable because their respective force particles are also indistinguishable. The standard model of physics combines QCD with QED and the weak force theory. It states that there are 6 quarks and 6 leptons and 12 gauge bosons, as well as their antiparticles. But only the up and down quarks, the electron, and the lightest neutrino are populous today. In the standard model, the entire system of matter and forces, except gravity, is encapsulated in a few simple equations, and is organized around one core principle, known as local gauge symmetry. Amazing.
Okay, now do you want to tell me what you told me before I told you to tell me slower?
Sure. Let's go back to the birth of the universe. Things are hot. Real hot. And things are happening fast. Real fast.
For the tiniest increment of time that is possible to talk about, 10 to the minus 43 seconds. The temperature was 10 to 32 degrees, and the density downright indescribable. At that instant, there was only one universal force and one type of elementary particle. But it wouldn't last. At the end of this instant, gravity separates itself from the union. At 10 to the minus 35 seconds, the strong nuclear force exits the union as well, and this triggers inflation, the event where the universe instantaneously grew into size, from tinier than an atom to an unknown large size. This expansion and subsequent cooling down to 10 to 27 degrees allows 6 different types of quarks to form. At 10 to minus 12 seconds and 10 to 15 degrees, the weak force and electromagnetism separate, and we have the 4 independent forces we know today. At this point, all 6 types of leptons have formed, including the electron. At 10 to the minus 6 seconds, up and down quarks have formed protons and neutrons. All heavy quarks have decayed. All heavy leptons have decayed. All antimatter has disappeared. And by the time the universe is only 1 second old, protons and neutrons are already getting together to form the lightest atomic nuclei.
We now examine a phenomenon which is absolutely impossible to explain in any classical way, and which is at the very heart of quantum mechanics. The famous double-slit experiment. To understand this experiment, we first need to see how ordinary particles, or little balls of matter, act. If we shoot small objects, such as marbles, at a screen containing a single slit, we see a pattern form where they went through the slit and hit on the back wall. Now, if we add a second slit, we would expect to see two bands directly behind the slits. Now, let's look at waves. The waves hit the slit and radiate out, striking the back wall with the most intensity directly in line with the slit. The line of brightness on the back screen shows that intensity. This is similar to the line the marbles make. But when we add the second slit, something different happens. If the top of one wave meets the bottom of another wave, they cancel each other out. So now there is an interference pattern on the back wall. Places where the two tops meet are the highest intensity, the bright lines, and where they cancel, there is nothing. So when we shoot particles such as matter through two slits, we get this, two bands of hits. And with waves, we get an interference pattern of many bands. Good so far. Now, let's go quantum. An electron is a tiny, tiny bit of matter, like a tiny marble. Let's fire a stream through one slit. It behaves just like the marbles, a single band. So, if we shoot these tiny particles through two slits, we should get, like the marbles, two bands. What? An interference pattern? We fired electrons, tiny bits of matter through, but we get a pattern like waves, not like little marbles. How? How could pieces of matter create an interference pattern like a wave? It doesn't make sense. But physicists are clever. They thought maybe those little balls are bouncing off of each other and creating that pattern. So they decide to shoot electrons through one at a time. There is no way they could interfere with each other. But after an hour of this, the same interference pattern is seen to emerge. The conclusion is inescapable. The single electron leaves as a particle, becomes a wave of potentials, goes through both slits and interferes with itself to hit the wall like a particle. But mathematically, it's even stranger. It goes through both slits, and it goes through neither, and it goes through just one, and it goes through just the other. All of these possibilities are in superposition with each other. But physicists were completely baffled by this. So, they decided to peek and see which slit it actually goes through. They put a measuring device by one slit to see which one it went through and let it fly. But the quantum world is far more mysterious than they could have imagined. When they observed, the electron went back to behaving like a little marble. It produced a pattern of two bands, not an interference pattern of many. The very act of measuring or observing which slit it went through meant it only went through one, not both. This led to many questions. What is matter? Marbles or waves? And waves of what? And what does an observer have to do with any of this? It was as if the electron decided to act differently, as though it was aware it was being watched. It seemed as if the observer somehow collapsed the wave function simply by observing. However, physicists eventually realized that any type of measuring device, no matter how small, always interacted with the electron, subsequently destroying the interference pattern. Werner Heisenberg, proposed a new uncertainty principle describing this. The uncertainty principle can be stated in terms of our experiment as follows. It is impossible to design an apparatus to determine which slit the electron passes through that will not at the same time disturb the electron enough to collapse its wave function, destroying the interference pattern. And it was here that physicists stepped forever into the strange netherworld of quantum uncertainty.
This is how we represent the down quark visually. The particle itself is a fundamental particle and is too small to be seen by any imaginable instrument of observation. So, we instead represent the properties that allow the down quark to interact. The central small dot represents the weak charge of the down quark. This charge, entirely separate of electric charge, gives rise to the weak nuclear force. This force causes the down quark to change into an up quark, and its typical range is much smaller than the diameter of a proton. Surrounding that is a volume depicted as purple for the down quark. This represents the electric charge of the down quark, which has a negative charge of 1/3 units. The electric charge is the generator of the electromagnetic force, which has infinite range, although the drop-off in strength is pretty dramatic as we move away from the quark. The larger volume of shifting red, green, and blue is meant to represent the color charge which generates the strong nuclear force. This is the force that holds quarks together in a proton or neutron. And the residuum of this force holds the protons and neutrons together in the nucleus of atoms. This force is 100 times stronger than the electromagnetic force, but its range is limited to about the size of a proton. This is how we represent the up quark visually. The particle itself is a fundamental particle and is too small to be seen by any imaginable instrument of observation. So we instead represent the properties that allow the up quark to interact. The central small dot represents the weak charge of the up quark. This charge, entirely separate of electric charge, gives rise to the weak nuclear force. This force causes up quarks and down quarks to swap flavors, and its typical range is much smaller than the diameter of a proton. Surrounding that is the volume depicted as gold for the up quark. This represents the electric charge of the up quark, which has a positive charge of plus 2/3 units. The electric charge is the generator of the electromagnetic force, which has infinite range, although the drop-off in strength is pretty dramatic as we move away from the quark. The larger volume of shifting red, green, and blue is meant to represent the color charge, which generates the strong nuclear force. This is the force that holds quarks together in a proton or neutron. And a residuum of this force holds the proton and neutrons together in the nucleus of an atom. This force is 100 times stronger than the electromagnetic force, but its range is limited to about the size of a proton. Gluons mediate the strong force. They have no mass, no electric charge, and no weak charge. So depicting gluons visually is a real challenge. To begin with, there are 8 of them, and each carries a combination of color charge. Secondly, there are no free gluons. They exist only virtually when 2 quarks interact. Third, since gluons have their own color charge, they generate secondary virtual gluons. These generate other gluons ad infinitum. This means there's such an ongoing storm of these gluons that the whole process is impossibly complicated. But undaunted, we press on. We know that when gluons cause 2 quarks to interact, the quarks swap color. And since color is conserved, the gluon must have at least 2 colors of its own. Next, we know that the strong force mediated by the gluons increases the strength as the quarks get further apart. This means the gluon field is what is called a flux tube, and this leads to a gluon shaped like a string. Putting all these ideas together leads to the depiction you see on the screen. Photons are the gauge bosons, the force carriers for electromagnetism. Whenever charged particles interact, photons are exchanged. They have no mass, no electric charge, no weak charge, no color charge. The epitome of almost nothing at all, and yet here is where it's at. Since they are responsible for all electron and proton interaction, everything we do in our everyday life, from moving a mouse to running in the park, relies on the exchange of photons. They are energy contained in shifting and changing electric and magnetic fields. Like all particles with no rest mass, photons travel at the speed of light. They cannot come to rest. Photons, in the range of visible light, carry just enough energy to excite a single molecule in a photoreceptor cell of your eye. This is our depiction of a proton. It is composed of 2 up quarks and 1 down quark, as you can see from the tiny rings of color near the center of the quark. The overall charge of a proton is positive, and so we have given it a gold shell. Note that we can simply add the charges of the individual quarks to get the charge of a proton. The red, green, and blue colors of the quarks represent the color charge which generates the strong nuclear force that holds them together. It comes in 3 different charges, represented here by 3 colors, and for different colors, force is attractive. The mediator of the strong force, the particle that is exchanged in an interaction, is a gluon. We represent gluon exchange as the occasional wispy string between the quarks. As you can see, the gluons have color themselves, and each gluon exchange causes the quark involved to swap color. Although we show quark motion inside the proton as leisurely, they are actually traveling close to the speed of light. Oh, protons taste sour, like vinegar and lemonade. This is our depiction of a neutron. It is composed of 2 down quarks and 1 up quark, as you can see from the tiny rings of color near the center of the quark. The overall charge of a neutron is neutral, so we have given it a silver shell. Note that we can simply add the charges of the individual quarks to give the charge of the neutron. The red, green, and blue colors of the quarks represent the color charge which generates the strong nuclear force that holds them together. It comes in 3 different charges, represented here by 3 colors, and for different colors, the force is attractive. The mediator of the strong force, the particle that is exchanged in an interaction, is a gluon. We represent gluon exchange as the occasional wispy string between the quarks. As you can see, the gluons have color themselves, and each gluon exchange causes the quark involved to swap color. Although we show quark motion inside of the neutron as leisurely, they are actually traveling close to the speed of light. This is how we represent an electron visually. The particle itself is a fundamental particle and is too small to be seen by any imaginable instrument of observation. So we instead represent the properties that allow the electron to interact. The central small dot represents the weak charge of the electron. This charge, entirely separate from electric charge, gives rise to the weak nuclear force. This force causes radioactive decay, and its typical range is much smaller than the diameter of a proton. The larger volume of shifting purple is meant to represent the electric charge of the electron. This charge is the generator of the electromagnetic force, which has infinite range, although the drop-off of strength is pretty dramatic as we move away from the electron. The electromagnetic force is how electrons interact with other electrically charged particles and with magnetic fields. These interactions make the structure of atoms and molecules possible. This gives rise to almost all of the complexity that we see around us. Gravitons are the as-yet undiscovered force carriers for gravity. Because of the great success of the Standard Model in describing the other three forces which exchange bosons, it is assumed that gravity has a gauge boson as well. Its properties have been extrapolated. It is a massless, stable, spin equals 2 particle that travels at the speed of light. Gravitons may not be constrained to the dimensions of space and time that we experience. Today we will talk about the mechanism that causes fundamental particles to have mass. If the electron had a different mass, then the orbitals inside atoms would be a different size, and the world would be a very different place. Let's begin by talking about the thing that physicists call a field. The need often arises to describe something that can have a different value at every point in space, like the air temperature, or like the wind velocity, or like the strength and direction of some force, such as the Earth's magnetic field. There are only 4 forces that we know of, and they are all described by fields that give their strength and direction at every point in space. But take note that a force field is something real. It is not just a number for every point in space. It has a physical reality. As John Archibald Wheeler said, it occupies space. It contains energy. Its presence eliminates the true vacuum. And in the words of Feynman, the field creates a condition in space. In classical physics, these fields were often thought of as continuous, smoothly changing entities. But quantum mechanics rejects the notion of continuous, and so fields become distributions of tiny field particles. And the strength of the field at any given point was nothing but the density or the quantity of field particles at that point. These particles are called virtual particles because they violate the conservation of energy rule for extremely short times in order to exist. They exist because of energy fluctuations allowed by Heisenberg, but they must disappear quickly because of the same principle. In force fields, like electric or magnetic fields, these field particles are called gauge bosons. They are the physical reality that occupies space as described by Wheeler. And while gauge bosons exist as virtual particles when generated in violation of conservation laws, they can exist as real particles too, if they are given enough energy to satisfy the conservation accounting. Most fields in science are generated by some source. An electric field is generated by the value of the field goes to 0, and Feynman's condition in space disappears. But the Higgs field is different in this respect. It still has a value, a physical reality, at every point in space, even without a source to generate it. So there really is no empty space anywhere. The entire cosmos is saturated with Higgs field all the time, everywhere. And because of quantum mechanics, this means there has to be a field particle. Enter the Higgs boson. Virtual Higgs bosons are the quanta of the Higgs field, and they interact with all particles except the photon, the graviton, and the gluons. The interaction between the Higgs boson and each particle is directly related to the rest mass of that particle. Since the top quark has the highest rest mass, it also has the strongest interaction with the Higgs. The electron is 300,000 times less mass than the top quark, so its Higgs interaction is much smaller. And the almost massless neutrino has only a tiny interaction. Since the Higgs permeates all space, any particle that interacts with the Higgs interacts with it all the time and everywhere. The Higgs particle acts like sticky bits that put a drag on other particles, and it is this